This is problem 132 from chapter 16. While the spring bridge is closing with a constant rotation of 0.5 radians per second, a man runs along the roadway such that when d is equal to 10 feet, he is running outward from the center at 5 feet per second with an acceleration of 2 feet per second squared, both measured relative to the roadway. Determine his velocity and acceleration at this instant. So we are going to use equation 1626. We're looking for the velocity of the man. The origin of the rotating coordinate system is O, so we're going to take 1626, make the subscript A's O's, make the subscript B's into M's, and that gives us this equation here. Now we're going to read through the problem and figure out what they're giving us here. So the swing bridge is closing with a constant rotation of 0.5 radians per second. So on the diagram here, on the picture here, they gave me a little XYZ coordinate system. We're going to use that. The coordinate system is rotating with the swing bridge. So the angular velocity of the swing bridge is the same as the angular velocity of the coordinate system. And we talked about that when we looked at these equations here. So we have capital omega here, lowercase omega here, but if you define your coordinate system so that it's rotating with your object here, then those angular velocities are the same. And if the swing bridge is rotating like this, that is k hat for the direction. So my angular velocity vector is 0.5 radians per second in the k hat directions, and they told me that it was a constant rotation, which means that the angular acceleration of the swing bridge is 0. So now the man's running along the roadway such that when d is equal to 10 feet, he's running outward from the center at 5 feet per second with an acceleration of 2 feet per second squared. So I got the 5 feet per second and the 2 feet per second squared. Now, if you're standing at point O and the drawbridge is rotating, you're standing at O, you're rotating with the drawbridge, you would see the man running away from you at 5 feet per second. So this is the velocity as measured by someone at point O and rotating with the drawbridge. Okay, so in your reference frame, the reference frame of the rotating drawbridge, you see the man running away from you at 5 feet per second. Using the coordinate system that they gave us here, that's in the negative j hat direction. So this is positive y, he's running away in this direction in the negative y direction, so that's negative j hat. This is the velocity of the man as measured by someone at point O rotating with the little XYZ coordinate system. And if you're speeding up, the acceleration is 2 feet per second squared in the same direction as the velocity. Okay, now let's see, both measured relative to the roadway, determine his velocity and acceleration. So we want the velocity of the man and the acceleration of the man as measured by someone who's not on the drawbridge. So maybe someone's standing on the shore. We want to know what they say the velocity of the man is. Okay, so let's see if we can start plugging things into our equation here. We're looking for the velocity of the man. This is the velocity of point O. So the drawbridge is rotating, but point O is not translating. Point O is staying at the same spot. So this is 0. We got our cross product here to do. Let's do the cross product first. So for just this term here, I've got my angular velocity of 0.5 radians per second in the k hat direction crossed with my position vector. This is the position of the man measured from point O. Point O is here, the man is here, a distance d away. D is equal to 10 feet. And let's put this over here. The position of the man with respect to O, that vector goes from here to here, and that's 10 feet in the negative j hat direction. Okay, I'm using the little XYZ coordinate system because that is what they gave me in the picture. But so I've expressed all these vectors with the coordinate system that they gave me here. But you could use a different coordinate system if you wanted to. And the vector, like this vector, the position vector, would still be pointing in the same direction. It would still have the same magnitude, but you would write it differently if you're using a different coordinate system. Okay, so we're going to stick with the little XYZ coordinate system. And let's just look over here. So right now, Y is going this way. X is going this way. And Z is going this way. Now, if you're going to use a capital X, capital Y, and capital Z, which in this problem we didn't even have to think about, but if you wanted to draw that coordinate system, I would make capital Z go in the same direction as little z. And capital X and capital Y, I would say like maybe something like this. Have X going this way and Y going this way. And then you have an angle here. That's not really a great picture. So all these axes are in the same plane. This angle is theta, and there's a relationship between theta and the time and omega. So this angle's changing at a rate of omega. So if you have your vectors expressed using the little XYZ coordinate system, you could then take them and figure out how you express them in the capital XYZ coordinate system. Okay, but we don't really need to worry about that here. And if you wanted to, you could even say at this point in time, you could make capital X going this way and capital Y going this way, and then it wouldn't matter. Okay, so we're going to use the little XYZ coordinate system that they gave us here. We don't even have to think about the fixed coordinate system in this point, in this problem. And our position vector, that's in the negative j hat direction. The distance between the man and the origin at this point in time is 10 feet. Okay, so that gives me 0.5 times 10 is 5. Radians per second times feet is feet per second. I have this negative sign here, which I don't want to forget about. When I do k hat crossed with j hat, that gives me a negative I hat, so the negative becomes positive, and that is in the I hat direction. So now I'm going to take this whole equation here and figure out what the velocity of the man is. So I have 5 feet per second in the I hat direction from doing the cross product, plus the relative velocity of the man with respect to point O as measured in the little XYZ coordinate system is negative 5 feet per second in the j hat direction. And let's write this as 5 I hat minus 5 j hat feet per second. Okay, now what this means is, let's say you have a bird's eye view of the situation. You see the man running along the drawbridge. He's running at a speed of 5 feet per second relative to the drawbridge. That gives you this here. But because the whole drawbridge is moving, you also have a component of the velocity in the I hat direction, so that's this way, perpendicular to the direction he's running in. Even if he was standing still, you'd still have a velocity of 5 feet per second in the I hat direction because he's moving with the drawbridge. Okay, now we get to find the acceleration as well. So now I'm going to look at equation 1629. Just like I did for equation 1626, all the subscript B's become M's, all the subscript A's become O's because this is point O here, and we're using M for the man. Okay, now probably a lot of these, some of these terms at least, are going to be equal to 0. So point O is not moving anywhere. Its velocity is equal to 0. Its acceleration is also equal to 0. This is going to happen in a lot of the problems in this section. Also, if you have the angular velocity of the drawbridge, if that's constant, then angular acceleration of the coordinate system is 0, so that term's 0 as well. So often in problems in this section, these two terms are both equal to 0. Okay, now we got some cross products to do here, so let's take care of those first. So for this, actually, look at this. We have omega crossed with the position here. That's the same thing that I have in parentheses here. So I'm going to take this first omega, which is 0.5 radians per second in the k hat direction, and I cross that with omega crossed with my position vector here, but I already know that's 5 feet per second in the I hat direction. So what's in parentheses I can replace with 5 feet per second in the I hat direction, then do omega crossed with that. So I have 0.5 times 5, which is 2.5 radians per second times feet per second. That is feet per second squared. Then I do k hat crossed with I hat. K hat crossed with I hat is j hat. So that's in the j hat direction. Then I have this cross product, which I'm going to do separately before I plug everything into my equation. So 2 times omega, omega is 0.5 radians per second in the k hat direction, so 2 times omega would be 1 radian per second in the k hat direction, crossed with the relative velocity, which is -5 feet per second in the j hat direction. K hat crossed with j hat is negative I hat. 1 radian per second times 5 feet per second is 5 feet per second squared. And I have the negative here, so that becomes positive 5 feet per second squared. Now I can take this equation and put everything together. So the acceleration of the man is equal to, this is 0, this is 0, this is 2.5 feet per second squared in the j hat direction, plus this is 5 feet per second squared in the I hat direction, and my relative acceleration here is -2 feet per second squared in the j hat direction. The units in each term are the same, so I'm going to pull them out and put them at the end. So this is feet per second squared. I have 2.5 minus 2 for the j hat term, so that's 0.5 in the j hat direction, and in the I hat direction we just have 5. So that is the acceleration of the man. If you're just standing on the bridge, you would say, and rotating with the bridge, you would say that this is the acceleration. But if you have a bird's eye view of the situation, or if you're standing on the shore, you would say the man has acceleration not just because he's running, but also because the bridge is rotating, and you would get this. Okay, so that concludes problem 132.